our grades is top secret.
It's so secret you don't even know them yet.
Yes, and not counting this class, okay, I think in general, overall, I think 50% of students here do not really care anyway, of their own grades.
Why do you say that? Why do you say that?
Why do I say that? Because when you look at, not this class, transfer classes are different because we are, you guys have a pretty clear goal of where you're going. But in many other classes, there are students who are taking classes only because they have to sustain their financial aid. So they don't really care about what they're learning. They don't really care about the grade as long as it meets the minimum requirements so that they can continue to receive financial aid.
Yeah.
I'm not against financial aid, just to make it clear. I think financial aid is a great thing because it helps, people to kind of continue with education. People who otherwise could not, get the education can get the education. I think it's a fantastic thing. But for people who exploit the system and only use financial aid to make a living, I have something against that. Yeah, I have to make it clear because otherwise I don't want people to think that I'm against financial aid. That is not what I'm against.
I wouldn't have gone for Cal Poly without financial aid, so
There you go.
I supported myself, throughout graduate school. So I was working outside of the university with a side job, the entire time. I got a lot of flack for doing that too. The graduate advisor threatened to kick me out of the program because I did not work as a research assistant and I have an outside job.
Wow.
And go like, why? Because I think the reason is because the idea is graduate students are cheap, inexpensive resources. So if your students are working outside, they're no longer available as a cheap resource for doing research.
right.
All right, let me check if the recorder is recording. All right, so let's go ahead and get started. So what I want to do today is kind of tie up all the loose ends and then move on to design the processor because we talked about some major components already. So I just want to kind of tie everything up, tie up all the loose ends and explain all the usual stuff. So up to this point, what we have talked about is the engine of computation. We talked about, just going all the way back, we talked about transistors, AND 2 gates, NAND 2 gates. We talked about how we can use NAND 2 gates to make all the other logic gates. Okay, so NAND 2 is really superior because it can be used to make every other gates that we need to use. And then we continue to talk about binary numbers and how to do arithmetics in binary addition, binary subtraction. Okay. And then we look at the binary addition and binary subtraction and go like, hey, the way we add can be done with logic gates. So it's no longer an arithmetic operation. It is now a logical operation, which we can use, AND, OR, and NOT gates to perform. So that's a great transition because now we can have gates to implement your adders and your subtractors. Okay, and then we talked about flip-flops, and we talked about SL latches, and those are also made out of NAND gates. Okay, but now we have small units of memory. In other words, with a D flip-flop, whether it's edge sensitive or level sensitive, we have a way to store something. It's like, okay, I'm storing this particular state here, okay, and as long as you don't tell me to change anything, I can maintain that. And that's a big move too, because now in addition to being able to compute, we can now also store. So that's kind of where we are at this point. So for computation, this, by the way, is a hyperlink. It gives you a logisim file that only has an ALU, but you don't need to download it because the ALU is actually described here as well. So I just want to kind of go over this a little bit, not a whole lot, just so that we know, generally speaking, what we have already gone over and what this design is going to do. So what we'll do is we look at this as an ALU. It is not drawn in the more traditional way. Traditionally, most ALUs are drawn like a Y shape. Okay, so it's usually drawn like this, where the inputs are coming in from the top, and then the output is coming out from the bottom. Okay, but I kind of draw it on the sideways, so if you want to look at it as a traditional ALU, just tilt your head 90 degrees counterclockwise. Then it becomes a conventional ALU. Yep, exactly. Counterclockwise, counterclockwise.
You just put the image.
Huh?
Click the image.
You can flip the image too, yes. And yes, so basically this is an ALU where the input is these two 8-bit pins, okay? A pin is nothing more than an interface. So if this is a procedure or a function, the pins are really just parameters, okay? They are how this particular design interface with outside, things that are outside of the design. We have an ALU enable. So the ALU enable ties into the enable bit of the demux, these two demultiplexers, and also this particular multiplexer. So you can see how this line kind of goes all the way around here to the enable pin of the multiplexer. It also goes to the enable pins of the demultiplexer and this particular demultiplexer. In other words, with one single pin, I can now say, hey, ALU, stop paying attention, okay? Do not drive the output and do not care about the input either. Don't do a single thing, save power. Okay, but if I have the enable turn on, become a 1, then the ALU becomes active and it will start to say, okay, give me something to compute and tell me what I want to compute. We have the same design here, okay, so we have the 5 or 6 really, really basic computations that is needed for any type of ALU. So starting from the top, we have addition, and then we have subtraction, then we have a right shift. This is a logical, this is bitwise NOT, this is bitwise AND, and this is bitwise OR. Okay, any questions about those individual operations? The right shift is a logical right shift. It shifts in a 0 into the most significant bit. Okay, because with that I can actually do arithmetic right shift using software. Okay, so I'm not too concerned about being able to do it in hardware. So I just do the minimum in this case in hardware. So in order to select which operation the entire ALU needs to do, it is the job of this multiplexer because, it's the jobs of the demultiplexers as well as the multiplexers. Because what's happening here is the operation selection, which is this pin here, it has 3 bits to select one out of 8 possible operations. I only have 6 individual operations here, which is fine. Okay, I don't have to use up all 8. So out of the 8 possible operations, I have room to implement 2 more. Okay, but I'm not too concerned about that. But these selection bits are connected to the demultiplexers as well as the multiplexer. In other words, only the operation that I'm interested in, let's say I'm interested in a subtraction, so only this line, only this particular mechanism is getting the necessary data for the input, and only the output of this one is going into the output pin through the multiplexer here. By doing this, I can save power. Because if I don't do something like this, if I don't use 2 demultiplexers to feed into the individual computation units, then every single thing, they will all do computations at the same time. Every single time I change the input, I will have 6 mechanisms all working at the same time to come up with a result. It's just up to the multiplexer to say, okay, I got 6 results here, which one should be the output of the ALU? It will just pick one of them. But the computations will be, 6 computations will be done all at the same time, which is a waste of time and a waste of energy. A waste of energy sounds like, well, that's not environmental, but that's not why it is bad. Okay, in the world of computation, it's heat as a waste that is the big deal. The limiting factor of how much computation power we can pack in a data center is not space, okay? It is not the electricity, it's not the supply of electricity. It is how much power, it's how much heat we can dissipate. Have I used a small room with a bunch of gamers as an example in this class? Yes? Okay, so that's basically the situation with data centers. Okay, how much processing power they can pack into a building is limited by how much heat can be extracted out of that building. Which also means something like this is preferred because if you can save power you are basically saving heat dissipation, and as a result, you can pack more processing power given the same amount of space. Yep.
What's the negation gate do in an LAU?
It's a bitwise NOT. So a bitwise NOT is basically the same thing as a bit NOT, as a normal NOT. So when you look at that NOT gate here, okay, let me just point to it. This one here. I'm going to use my document camera. Just need a little bit of time to set it up. I still have my Scotch tape attached to the LED light. Apparently it's holding up just fine. I will upgrade it to duct tape, when this falls apart. And if duct tape starts to fall apart, then I will use Gorilla Tape. Have you guys ever used Gorilla Tape? Do you know what is Gorilla Tape? Good stuff. It's good stuff that when you watch movies and people want to kind of cover somebody's mouth, they always use duct tape. No, use Gorilla Tape. Let's see, go to multimedia, DLC. There we go. I changed the height of the camera a little bit, so now we can actually see a little bit more than before. There we go. Try to move the cable out of the way. There we go. Have a little bit of a keystone distortion. This is not done in software, it's all done in hardware. The human zoom. I remember when point and shoot camera used to be all fixed lenses. So when they first came out with the ability to zoom, the commercial was okay, without the zooming ability, so they show the photographer who has to keep walking back and forth to control the size of the image, and then this guy just use a zoom feature and I don't have to move at all. But real photographers only use fixed focal length lenses. Okay, so getting back to this one here. What was I? Oh, the NOT gate. That's it. So when we have a NOT gate that has an 8-bit thing, in other words, we have on this side an 8-bit input, and on this side we have an 8-bit output. What it really is the same thing as having the 8-bit input. Okay, my pen is dying on me. Okay, it is dead. It's dead, Jim. And I'm gonna steal one from the drawer. There's plenty more. Okay, so it's really the same thing as going through a splitter first. Split it 8 ways. 1, 2, 3, 4, 5, 6, 7, 8. And have each one having an individual NOT gate, like that. And have a merge at the output to merge everything back into a single wire. So an 8-bit bitwise NOT, which is what I use in the design here, is really the same thing as this. Those two constructs are the same. And that's why when you have AND gates, you can actually specify the bit width to be more than 1, because you can take in more than 1 bit from the input and more than 1 bit from as the output. It can also give you more than 1 outputs. Yep.
So are you just changing all the ones to zeros and all the zeros to one?
Yes. So it becomes a bitwise NOT. It's the same thing as the tilde symbol in C and C++. In C and C++, you have the tilde symbol, this guy here. So when you say tilde x, it is the bitwise NOT of x. For each bit inside the integer, if it's a 1, you turn it into a 0. If it's a 0, you turn it into a 1. So this is basically doing exactly the same thing. It's a bitwise NOT, but applied to multiple bits. Is that okay? So the bitwise end is the same thing. Okay, so when we go back to the design here, this is a bitwise end, which also has 8 bits for the inputs and 8 bits for the output, and this is bitwise OR. Those operations are really useful because without those, it becomes really hard to perform certain operations. So bitwise operations are actually quite crucial to the design of a processor for low-level operations. All right. Any other questions about this particular design? This is the ALU. It's a very simple ALU. It doesn't even have the ability to compare. Okay, so we'll add the ability to compare and stuff like that later on. But at this point, it really is just a simple ALU. It can do calculations, and that's about it. Any questions about this? Okay, we have looked at this, several times already. Just slightly different from the previous times, but pretty close. Go ahead.
What is the upsell?
Operation selection. So it selects which operation out of these 6.
How does that work? Have we seen how that works?
Yes, because upsell connects to the gray pin here, the pin with the little gray dot, and this one with a little gray dot, and this one with a gray dot. Do you guys remember with a demultiplexer or a multiplexer, what is the name of the pin that has a little gray dot on top of it?
You choose it. So that pin can choose which.
It's a selection.
Yeah.
It's the selector. So that's So we did talk about that.
So that's a 3-bit pin input.
Yes, it's a 3-bit pin so that you can select one of the 8. Because 2 to the power of 3 is 8. So as a 3-bit selection pin, it can select one of the 8 things. The only difference between a demultiplexer, which is denoted here as DMX, versus a multiplexer, which is MUX, is a demultiplexer has one single input and multiple outputs, and then the multiplexer is the reverse. You have multiple input and only one single output. It's the direction. That's the only difference. Is that okay? All right. Now, for the purposes of the exam on next Tuesday, I found a way to print out, the necessary help files from inside LogicSim. Okay, I'm not going to repeat what you have to do because I think I got it recorded in the lab session of Tuesday. So for those of you who are interested, you can watch that video, or if you were in the lab during that time, you probably knew how to do it already. Okay, so it's a really great resource because now you can say, okay, I need to be reminded what a demultiplexer does and what those pins are all about. Just print out that page, bring it with you, then you have reference material for individual components. Okay, so the next thing we talked about are the registers. Now we don't want to use a single register. Now once again, this is a hyperlink. If you click on this one, you can download the LogicSim file corresponding to this diagram. In other words, if you want to play with this, you don't have to do everything on your own unless you want to. You can just download the LogicSim file and then just play with it. But the circuit is like this one. Okay, it's a little bit different, but it's very similar to what we have talked about so far. We have a decoder, okay, and the decoder can basically say which register has to pay attention for update purposes. And I forgot one important thing in this diagram. The data line is not connected. So none of these can actually be updated, but they will all be connected to one single 8-bit port. Okay, so this is a fairly important omission, but they're all going to be connected to one single data port as the input, but as a register bank it has 2 possible outputs. So these 2 are the possible outputs: register 0 out, register output 1, and output 0. So those are the 2 potential outputs. Each one has its own multiplexer. In other words, you can choose any one of the 4 registers to be the first output or output 0, and you can do the same thing for the second output, any one of the 4 registers as the second output. Okay? And they do not interfere. You can choose the same register to be presented as both of the outputs. It's not a problem. Okay? And then each output has its own enable pin. So this is an enable pin for this particular output. This is an enable pin for this particular output. And each one has its own selection. So they're not tied in any particular way. In other words, when you look at this diagram, comparing this to the ALU, this one gives you a lot more fine control over the individual output of the register bank, because that is actually needed. Because registers, the ALU is fairly simple. Okay, what does an ALU do? The name of an ALU is arithmetic logic unit. So what does it do?
Does arithmetic and logic.
Subtraction, multiplication, well, possibly multiplication, logical and stuff like that. Okay, so basically just computations. You give it something to compute, they give you the result, and that's it. So that's why most of the control pins are tied together. The selection pins are tied together. The enable pins are all tied together because as a unit, it's either enabled, yes, let's do some computation and tell me what you want to compute, or okay, just turn me off and I don't want to do anything. Okay, but the register bank is different because registers are used for many, many different purposes. The first purpose is obviously, okay, you can supply values to the ALU and you can store the result after the computation. Okay, that's the first and really obvious way to use registers. But it also has many, many other purposes, and that's why we don't want to tie in everything together and just say that, okay, we are designing the register bank so that we can supply values to do computation and then store the result after the computation. That's one way to use the register bank, but only one of many ways to use a register bank. Are we okay so far with why the register bank has so many little control lines spilling everywhere? Okay. All right, so the next topic has to do with memory access. Because at this point, with question number 7 of the practice exam, okay, we can only do computations inside the processor. We cannot even store the result of the computation into memory. You only have, 4, 6 registers to play with. So you can only do certain types of computation, not really a whole lot of computation. So at some point, you want your processor to be able to access memory so that you can store the results back into memory. You can read numbers to compute from memory. And also with a von Neumann architecture, you also want to be able to read instructions from memory, because that's the one thing about von Neumann architecture is instructions are stored in memory just like the data you're going to process. Are we okay so far with those concepts? Why the processor needs to access memory? Okay. So when you access memory, what kind of pathways are we talking about when a processor needs to talk to memory? So these are the ways these are by function. I'm listing how components can interact as far as, just components in interaction amongst components. So this part just talks about how the ALU, the output of the ALU has to be able to connect to the register bank input just so that we can store the result after computation into a register. Does that make sense? It is in question 7 of the practice exam, this one. Is that okay? All right. So the second one is how we want the input of an ALU connected to the outputs of the register bank. That makes perfect sense too, because something has to supply the values for computation, and registers are a very natural way to supply those values for computation. Is this okay? This is also in question number 7 of the practice exam. Now this part is not in the question. Okay, so we are starting to talk about the memory access, or the memory bus, which includes the data bus and the address bus and the control lines. One register bank output needs to hook up to the data bus of the memory. This is what allows us to store the result or the value of a register into a memory location. Do you think that is important? You have 8 registers, but you have 16 gigabytes of memory, right? Yep.
Can you explain what a bus is?
A bus is just a term to refer to a group of lines, a group of individual lines that together serve a particular purpose. So a data bus in this case is really what we see as a single wire in Logic Sim, but inside it has like 8 wires bundled. But those 8 wires are all closely related because one is bit 0 of the data bus, one is bit 1, and then the last one is bit 7. But together they serve one single purpose, which is to allow the specification of data on that bus, okay? But they can go in either direction. So the term bus is typically just used in that way. It's a collection of lines that serves a particular purpose. Okay. We also want the output, one register bank output, to connect to the address bus of memory. In other words, we want to be able to use one particular register to specify a location in memory, because this allows the specification of an address. And that is, it's actually really kind of useful, because this allows flexible access to memory. Because if you can use a register to control the memory bus in terms of the address, now you can open up all kinds of possibilities. And the last one is allowing the data bus to connect to the registered bank input. This way we can read the content of a memory location and store it back into a register, because then we can use that register for computation. Okay? So the way I designed this processor is definitely a RISC type. In other words, I'm trying to minimize the amount of logic and the amount of silicon to get the job done. Okay, so something that you can do with one single instruction with a cisp architecture, this architecture may take 4 or 5 instructions, but it will get it done. It's just not as convenient. So from the function description, which is this part here, we can now see the interconnection. The interconnection are, these things are all connected. The output of the ALU, registered bank input, and the data bus are somehow connected. Okay. The next one, the next group, consists of one input of the ALU, one output of the register bank, and the data bus. They're also connected. And then the last one is the other input of the ALU, the other output of the register bank, and the data bus. They're also connected. But now we have a problem, especially when the data bus is, as far as the data bus is concerned, because the data bus is bidirectional, which means sometimes you want the processor to drive the data bus, which means the processor is what is putting content on the data bus because you're writing to memory. Other times you want the opposite direction, where the processor wants to read from a certain location of your memory chip. So you want the memory chip to drive the bus, and the processor is nothing more than just listening to the bus and go like, okay, what is the content of that location again? And the memory device has to drive the bus. Okay, so those present kind of interesting problems, because we can potentially have a bus fight. The bus fight is where the data bus is connecting to something that can be driven by something else. This particular one can potentially have a bus fight, because the output of the ALU can drive this connection, and then the data bus can be driven by the memory chip. So we can potentially have a bus fight here. We can also potentially have a bus fight with the next one, because with this one, the register bank output 0 and the data bus can both be driving the line, and we don't want them to do it like this, right? So this can potentially have a bus fight as well. The last one does not really have a bus fight issue by itself, because we have 2 potential inputs and only 1 potential output, because the address bus cannot be driven by the memory chip. It doesn't make sense, right? It doesn't make sense that your memory chip will tell the processor and say, hey, processor, read this location. The processor is the one that has to control it and say, okay, I want to read that location. Give me the content of that location. As a result, the address bus is always driven by the processor. The register bank is what is driving. The address bus is actually, from the perspective of the processor, is an input pin to the memory chip. And the ALU is also having just an input. So you have 1 single output and 2 potential inputs. There are no bus fights. So we don't have an issue with the third one, but the first 2 potentially has a situation where we can have a bus fight. So how do we resolve these bus fight situations?
4? Using like 4 gates, or?
Well, we have something called multiplexers and demultiplexers.
Okay.
And those are useful for resolving situations like this, because when you can potentially have multiple things driving
It restricts
a connection, then you can use a demultiplexer You can select one of the multiple inputs and say, okay, this time I want you to connect to the other side. When you have a situation where you have one single input and multiple outputs, then you can use a multiplexer by saying, okay, no, I got it the other way around. One input, multiple output is demultiplexer. So you can say, okay, one input, let me see who should be getting this particular input. So that's how we're going to solve that problem. So the way we solve this problem, we can draw this in LogicSim today, is to have the register bank input mux or multiplexer. The potential inputs at this point is the ALU output and the data bus. In other words, we'll have these two as potential inputs, and the output is going into the input of the register bank. So this way you can say, okay, how are we updating a particular register? Are we updating the register based on the output of the ALU, or are we reading the content from memory, and as a result we are using the content of the memory location to update that particular register? So we have multiple input, one single output, it is a multiplexer. The second scenario has to do with the first output of the register bank. It is a demultiplexer because we have two potential outputs and one single input into the demultiplexer. The potential outputs in this case is you can go to the input, the first input of the ALU. You can say, okay, the output of this register bank is hooking up to one of the inputs of the ALU because we are trying to perform a calculation. Or you can also hook it up to the data bus where you want to store the content of a register into some location in memory. And then the last one has to do with the other output of the register bank, where one thing you can connect to is one of the inputs, the other input of the ALU, because you are about to perform a calculation. And then the other potential output is the address bus, because we want to use this particular register to specify a location in memory to access. So conceptually, are we okay so far with all of these concepts? I haven't drawn a picture yet because I don't want to do it yet, because there are other things that needs to hook up to the data bus as well as the address bus. If I were to draw a picture at this point, it has to be modified later on to accommodate the program counter and a few other things. Yes?
Why can't we just use the enable pins instead of these?
Very good question. The enable pin can be used, but then you'll be putting additional restrictions on what operations cannot be performed at the same time. Because the use of the enable pin means, okay, everybody shut up except for one, right? But that means, out of the many things that can be interconnected, so let's say you have 4 things that can be interconnected. If you connect everything and resolve conflicts by output enables, then only one operation can occur at any time. So one thing can only talk to the other one thing. But on the other hand, if you use the concept of multiplexers and demultiplexers, then you can create a cross-hedge network where you can say, okay, A and B, you guys talk, C and D, you guys talk. So you can have both operations going on at exactly the same time. Whereas if you use the other approach, then you can only have one of the A, B, C, D talking, and potentially probably one to be listening. But they can all be listening at the same time. But then you have more limitations. Is that okay so far?
It'd be slower, wouldn't it?
If the
to
difference
get the same thing done, you'd have to do something first, then do the next thing. Do something.
Right. The approach of using output enable is going to be slower. In terms of networking technology, this is basically a hub, a network hub, versus a network switch. I'm not sure how many of you know networking technology. No? Okay. I can give you a really quick introduction to that. A hub is the basic way of how Ethernet works, at least from the good old days. So Ethernet is called a CDMA / collision detection. Okay, I have to look up the terms, but basically they all hook up to the same wire. Okay, just think of multiple computers hooking up to the same 2 wires. So when two devices try to talk at the same time, they have what we call a collision detection mechanism. To basically say, okay, I'm trying to listen to myself, But since I am driving the Ethernet cable and somebody else is also driving the Ethernet cable, it becomes garbled. Okay, I'm expecting to hear on the line, 0110, okay, because that's what I'm transmitting. But I'm getting back, by sensing the line, I'm getting back like 0001, okay, which is not what I'm trying to transmit. So that means I have a collision with somebody else. And in cases like that, in terms of the Ethernet, they have an algorithm of random backup time. So the devices that they're all trying to transmit it at the same time, they will use a random number to determine, okay, I'm going to wait another 2 milliseconds, and then the other device would say, I'm going to wait another 5 milliseconds to retransmit. So as a result, you have the conflict resolved because one will retransmit in 2 milliseconds, get it done, and then the other one will retransmit in 5 milliseconds, and causing no conflict. Now this works really well when you do not have a whole lot of devices hooked up to the bus, because when the number of devices increase hooking up to the same bus, the chances of a collision increases, but it's not gradual. And then the chances of being able to resolve that decreases also exponentially. So you have a double problem because the chances of collision increases, but the chances of we can resolve it by a random number is also less than before. And that's why it's inefficient. A switch, on the other hand, which is what we use these days when we talk about Ethernet, they are all basically coming out of a switch. A switch, on the other hand, is a device that is kind of like a cross network. So it would look at incoming packet and say, okay, let me see which way you're supposed to go. Oh, you're supposed to go that way. And then the next packet, you're supposed to go that way, and so on. So there's no collision whatsoever. Same thing over here. If you use the approach of output enable, you're basically using you're using one single resource to distribute the signal. So everybody has to shut up except for one device. You're only allowing one communication to go through at a time. But when you use multiplexers and demultiplexers, you are allowing potentially multiple conversations to happen at the same time, and therefore increasing the efficiency of the processor. So is that kind of answering that question? Okay. So the next real big concept to talk about is the program counter, otherwise known as the PC for most architectures, but Intel prefers to call it the instruction pointer or IP, so they mean exactly the same thing. This is a particular register, not really unlike the other registers that we have talked about, but this is a special register. This particular special register determines the memory location of the next instruction. Okay, and therefore it is called the instruction pointer by Intel. It's also called the program counter by most other architectures. It is typically not a part of the register bank because a PC requires very specific pathways. If we put the program counter into the register bank itself, then we'll be limiting what really can be done at the same time when the program counter needs to be used. And that's why it's usually outside of the register bank. It is considered a special register. And in most architectures, you don't have direct access to the content of the program counter. So in the normal flow of a program, you just want to execute the next instruction, and then the next instruction, and then the next instruction. So as a result, the program counter is kind of like the counter mechanism in your music box homework assignment. You just need to increment, keep going up by one, going up by one, going up by one, because this is how you execute the program sequentially. On the other hand, if this is the only thing that the PC can do, then you cannot branch. There's no way for you to implement anything that has branching. Now, branching sometimes is obvious when you are talking about a conditional statement. Branching is obvious, right? Because you go in, as one single branch, as one single thread, and go like, okay, now we can branch. Which way are we supposed to go? Well, that's kind of obvious branching. What about an infinite loop? Does an infinite loop involve branching? Well, it does. Okay, in a way. Okay, it is a branch because at some point you have to go back to an earlier instruction. That is branching as well. Okay, it's not conditional branching, which means it is not always. It's not sometimes going back and other times not go back. But the act of going back to an earlier location means that you cannot just keep incrementing the program counter. You have to be able to reset the program counter and say, I want you to be exactly this value so that we can go back to a certain location earlier to perform looping. So even if the loop itself is infinite, you still need branching. because you have to be able to go back to an earlier location. All right, so as a result, it is important that the program counter to be able to be modified directly. We want to be able to say, hey, program counter, I want you to be this specific value now. Okay, instead of just going like, okay, keep incrementing. And this allows the altering of the execution path. It is not sequential anymore. Now, based on the function of the program counter, we know that it needs to be able to drive the address bus. As a result, it also needs to be one of the inputs into the multiplexer of the address bus. And this is why earlier I only mentioned up to this point, at this point. Because now we also have one more thing hooked up to the address bus in addition to the register bank output 1, as well as, okay, I think that's the only one. Yeah. So in addition to register bank output 1, we now have one more thing that needs to hook up to the address bus. Okay. Are there any questions about this particular write-up here? No questions? Okay, if there are no questions, we're going to take all of this stuff here and then start to modify, to put things together. Okay. So let me show you guys how to do this, because it's really kind of cool because you can make your own library of parts in multiple files. So I just right-click on this one and save link as, and put it into, I guess this folder is fine. I just put it into my downloads folder. And the same thing over here. Save link. There we go. All right, so now I can go back to a command line prompt and start up a LogicSim. Oops. There we go. And generic. There we go. All right. So when you start up a project and you say, okay, I need to use a particular component that I have already designed in some other project file, there's a way to do it. You can go to Project and say Load Library, and then click on Not Built-in but LogicSim Library. This allows you to specify the path to a particular circ file, CIRC file. And the one that I'm interested in is the one that I have just downloaded earlier. One is the ALU. So you say open, and you can see how ALU, which is a component of that particular LogicSim file, is now available over here. It only has one single component, okay? So the file itself becomes the category name, and then all the components except for main becomes subcomponents of that particular category. So this allows you to create your own collection of libraries so that you can reuse components over and over again, and yet not have to copy and paste everything into one single file. Okay. All right, so we'll just pick out one ALU like this, and we'll probably need to zoom out a little bit because we got some other components to hook up to. And we also want to import from the other one, which is the register bank. So I go to Load Library again, go to LogicSim Library, and this time we go to Register Bank, click Open, and now we have Register Bank as a category, and under the category we have the actual part. Okay. All right, so we have the two components that we have just talked about in today's lecture, and then the next thing we want to do is to create the program counter and the address bus as a pin, so that we can see, okay, how do these things connect. All right, so we'll draw some connections between these two first. Okay, so we have the ALU on this side, the register bank on this side, and the obvious things that we have to do. Remember what we talked about? These are not named correctly. I should have named this in0 and in1, instead of in1 and in2. But it's okay. Okay, one is the first one, the other one is the second one. I don't want to do this, do I? This would not be what I want to do. I don't want to draw a straight line because I need a mux. I need a mechanism so that the output 0 of the register bank can sometimes drive the ALU, and other times it can drive something else. Okay. Remember what we talked about a little bit earlier? Okay. So we have a data bus that is sitting somewhere else that I want to drive. So I want to remove these lines. Let me just increase the zoom here because I can afford to at this point. So we'll go to the plexers, and we can choose a demultiplexer in this case because we have one single input to feed into multiple outputs potentially. Okay. And at this point we only have two things to do, okay? But then we also want to say, but how do we update the program counter? The program counter is a register, and I know it needs to be updated directly sometimes because we don't want it to auto-increment. Yep?
You have to do,
I can use one of the registers from the register bank, one of the outputs of the register bank, and feed it into the input of the program counter. I can do that.
so is it like a loop?
It's not exactly a loop because the program counter output is always connected. Well, if it is needed, it always needs to be hooked up to the address bus. So it's not exactly a loop. Okay. So which also means I need more than one things to be hooked up to the output here. So I would need 2 pins for the selection. And I really need to fix one thing first because remember what I said in the register bank is not done yet. Actually, I think this one is done. Nope, it's not. I forgot to specify the actual port to specify the data, so I need to finish that first. It won't let me change it because it's a part borrowed from another file. So let me fix the other one first. Alright, so let me fix this first because the data port is not connected to anywhere. So the way we do this is we hook up all of them to the same port because we have the decoder to specify which register should pay attention already. So all of these can be connected together into a single input pin that is 8-bit wide. So there we go. The direction is off because I changed that. And we want to make it 8-bit wide, and we'll just call that register in. There we go. Which also means I need to change the appearance of the circuit because we have one extra thing in the circuit now. And I have no idea where it put it. I think that's new. This is register in, select, enable, and this is register in. This one is okay because I know we cannot change that one. The mapping doesn't seem right to me. I'm missing a port. Sorry? I'm missing this one here.
What's the one below out 0?
Below out 0. Oh, you're right. Okay, so it put it here. Thanks. This label is incorrect. It is a register input select. Oh, it won't let me append it either. There we go. Alrighty, save the file. Okay, so I need to do several things. One is to update the ones on Moodle so that the stuff in Moodle is updated and correct, and then we'll incorporate this new version into the design too. So first thing first, update Moodle. And we'll go ahead and change the picture too. So I'm going to get rid of this picture. We'll generate a new one. And then we'll update the file corresponding to this link. Right, okay. And I'll also include a picture of this. Not this one, but the other one over here. Okay, so to generate a new picture, this is something that you might also want to know in order to prepare for the exam, because you might want to print out certain circuits. So what you do is you can print it directly, but if you want to incorporate this into some other notes that you're writing, you can export the image into a PNG file. So we want to put this into register bank PNG. And now you have a PNG that you can include into any document that you're writing. So in this case, I just have to do this inside Moodle. Go pick out that PNG file, register bank.png, upload it. Overwrite the original file, specify this is the schematic of a registered bank. Click Save Image. So if you check Moodle right now, it should be updated. It's kind of like a book, but it's a live book. I can keep changing it. Okay, but the big question is, when I go back to LogicSim, go back to the one that refers to the register bank, when do you think it's going to get updated? This is definitely not updated yet. Well, so I want to right click on it and say reload library. Ta-da! So you just have to reload it, then you can incorporate the newer design into your overall design. So when we go back to main, now it has the necessary ports, which is great, because that's what we need. So once again, over here we have a multiplexer, and okay, the multiplexer needs to be 8-bit, needs to have 8 data bits. Okay, so that fixes that problem. Which one you connect to really does not matter. Like which output is output 0 and which one is output 1 really does not matter. So in this case, I'm just going to lay out to the point where it is easier for me to do the layout here. So output 0 goes into the input of the ALU, and then output 0 would go somewhere else. Okay, we'll describe where it's going to go. And then this one here is going to go to the data bus. But at this point, I can't really draw the data bus yet, okay? Because the data bus being a bidirectional bus means that it requires some special consideration, because sometimes it can be seen as an output pin, other times it can be seen as an input pin. So it's kind of one of those kind of awkward thing that we have to deal with, but later on. Okay. The enable pin of the register bank for output 0 is independent. I'm not going to deal with it yet, okay, because that's something that we can control later on. We need another demultiplexer for output 1, because output 1 can connect to the input 2 of the ALU, but it can also connect to the address bus of the memory chip. So that's why we need a demultiplexer as well. So we'll specify another demultiplexer with 8-bit as the path. And this one connects to the second output of the register bank, where the first one connects to the input of the ALU. And I'm not hooking up the rest of the line yet. Are we doing okay so far looking at this picture, which reflects some of the stuff that we talked about earlier? Is that okay or not? Well, first of all, are we still preserving the ability to feed registers into the ALU for computation purposes? We're still able to do it. It's just that now we have a demultiplexer sitting between the two components. So you have to configure the selection pins correctly first before the ALU field can work. Okay, but otherwise, the functionality of question number 7 in the practice exam is still preserved here. And then the other thing we also need to do is to control what goes into the input of the register bank. So for that purpose, we need a multiplexer because we have multiple inputs going into one single output. So we need to hook up a multiplexer to the input of the register bank, and we need to fix the width of the data at this point. Okay. Which two things can potentially feed into the input of the register bank? We talked about this a little bit earlier. One is the output of the ALU, because we want to be able to store the result after a computation. What is the other one? From memory, very good. So it's from the data bus. Okay, very good. So far we have two ways to change the input of a register. So we want the output of the ALU to be one way to change a particular register, and then we have the other way being the data bus. But the data bus is bidirectional. So as once again, as I said a little bit earlier, it's a little bit hard to specify because it can both be seen as an input pin or as an output pin. So that makes it a little bit tricky to specify. Are we still doing okay so far at this point? And then we need a program counter. Remember the program counter thing? Okay, so how do we implement a program counter? We go to memory, we pick out a register. Okay, this part is the same as your music box homework assignment. We need an adder. And for this particular adder, we just want to add 1 to it. Okay, here's a big question. Why can't we just use the ALU to perform adding 1 to the program counter?
Because that'd be a waste of an ALU.
Yes, because then when the program counter is incrementing, you cannot do any other computation. So now you are funneling all the computation through the ALU, even for something as simple as adding 1. So you don't want to create those critical paths unnecessarily. So that's why we don't want to use the ALU just for adding 1 to the program counter. The program counter has its own auto increment mechanism, so that we don't need to. Well, first of all, we don't need to use another demultiplexer to go into the ALU. Okay, so this part should be fairly familiar because we have done this many times already. So once again, we have to specify adding 1. And to specify adding 1, you have to specify one input to be a 1, the other one input to be a 0. So we'll just specify the carry in to be a 1. And then we can now specify the other input, which is now going to be a bit wide, to specify a 0. So there we go. And then the register itself is feeding into the other input of the adder. And then the result of adding is going back, but not straight into the D pin or the D port of the register, because remember, now we want to have an alternative way to update the program counter. Okay, we don't want the program counter to keep auto incrementing all the time. We want to have another way to update it. Say again?
So if I can go into another mux?
We don't. That demux is already here, but it needs a mux to combine the inputs into one. Okay. So we can use a mux here. Go to plexers, specify a mux, and say, okay, the output of the mux is going to go into the register. Okay, change it to 8-bit wide, like so. And we already have that here, so we just go from here to here, and then this one from here to here, okay? And I'm not too concerned about the control pins just yet, so I'm not going to do anything about the control pins. This one, which is the output of the program counter, let's label this. This is my program counter. So this line here, which is coming out of the program counter, and also this one here, which is coming out of output 1 of the register bank, they can both be driving the address bus, which means now we need a multiplexer to combine the two inputs into one single output before it becomes the address line. So we specify another mux over here, and here. Yeah, I know, it doesn't look very artistic. Okay. And then the output of this will drive the address bus. Okay. Are there any questions at this point about this particular design? It is almost the same thing as the one in question number 7 of the practice test, except now we have additional demultiplexers and additional multiplexers, and also the program counter to make the design a little bit more complete. Is that okay? Yep.
Why did the program counter and the output 1 of the register bank go to the same?
Say that one more time.
Why did the register bank output 1 and the program counter go to the same multiplexer?
Why we have this path and this path?
Yes.
Okay, because this is going to hook up to the address line of the memory chip. In other words, the reason why we want, okay, this one is kind of obvious. Okay, the program counter needs to hook up to the address bus because the program counter determines what is the next, where is the next instruction to execute.
Okay, I thought you said data bus, that's why I was confused.
Oh, okay. I might have misspoken. Misspoken. But then the other one allows us to use a register to control which locations we want to access, which is actually very important as well, because that will give us the ability to access different locations in memory, but from the same instruction.
So how would it choose between the program counter or the...
That's a good question. How would it choose between the program counter versus the this other input here? So it all depends on the selection pin here.
Just coming from where?
That selection pin comes from, what do you think, where do you think it comes from?
Register bank?
No, not register bank.
From the
As a processor, we're still missing one big chunk here. The music box is missing. So one of the output of the music box is hooking up. So the music box is not going to be a lot bigger. In other words, when you look at the width of the drum, it's no longer 8 or 9 bits, which is what you need for the 7-segment display. It's not going to be 20 bits, 30 bits wide, because now we need to control all of these enables, all of these select pins of all of the multiplexers and demultiplexers. Is that okay? But I'm not too concerned about the orchestration yet, okay? In other words, what I'm trying to do here is I'm really just assembling an orchestra. I'm just picking out the instruments. I'm balancing out the bass versus the treble versus the mid-tone and stuff like that. I don't even have a music score to play yet, okay? I'm just saying, okay, I'm gonna need a whole section of violins over here, a whole section of flutes over here, and so on and so forth. Is that okay? So the orchestration, which is done by the exercising of these control lines, is not even in the picture yet. Is that okay? All right, so the next thing we want to do is to say, okay, now that we have something to hook up to the data bus and something to hook up to the address bus, how do they hook up, okay? So let me, if I can do this, I'm pretty sure I can. So we go to memory, and we pick out a RAM module, and then we just kind of slap it. I have to slap it where there's exactly a pin. Okay, give me a space here. There we go. Okay, so now I can put this a little bit spaced out over here. Okay, the address line is easy. The address line is always acting as an input pin. So the address line just hooks up to the output of this mux and we are done. The data line is going to be the tricky one because the data line coming out of the memory chip is bidirectional. So now we look at this line here and go like, okay, so how are we going to hook it up? Okay, let's figure out which lines need to hook up to the data line here. This one here needs to hook up to the data line. Okay, and I think there's one more. Nope, that's it. That's the only one. No, that's one more because we need to be able to read memory into a register. So this part, this mux here, or this line, the second line to this mux also needs to hook up to the data bus. Okay, and then we have a problem. The problem is not shown here because we haven't hooked up this port yet. Okay, but when we do the simulation, it can potentially have problems now. Why do you think we can potentially have problems? Let me zoom out a little bit so that we can see all the major components. And I will go into simulation mode because this is an easy way to see how a particular line is connected. So you can see this line connects to the input of the mux on the left-hand side. That's not a problem, okay? Because that mux is specified in an input pin. It doesn't drive the line. But we have two potential things that can drive this line. The demultiplexer can drive that line because that's the output side of the demultiplexer. And then the memory chip can also potentially drive this particular line because when you are specifying a read operation, the memory chip is driving the line. But this is not a problem. It's not a problem because I have control over the demultiplexer. I can disable the output of the multiplexer so that it doesn't do anything. I can also control the memory chip because if you specify a 0 for the LD port, it becomes a write operation, and then it doesn't drive the data port anymore. If the RAM chip is not selected, it doesn't drive the data port. So we may not need any additional circuitry so that this would not end up with a bus fight. But there is a potential for a bus fight here because we have two things that can drive the data bus at the same time. Are there any questions about this part? No questions?
So it's going to be handled by the selection on the Demux and the load?
Correct. So now the key to make sure that there's no bus fight is the coordination between this particular select pin of the memory chip and also the enable pin of that particular demultiplexer. If they're not on at the same time, then we cannot possibly end up with a bus fight. Is that okay? All right, so I'm going to save this design because this is as far as I want to go as far as the processor is concerned. So I'm going to save this design into probably not the downloads folder, but we'll put it into here. CPU design. And the reason why I have to stop at this point, pause with I have to kind of we have to stop the design of the processor and work on something else. Because this particular mux here, okay, what can be used to update the processor? This is not the entire story, okay? Because if you look at all the possible pathways here, we can now have infinite loops. Yep.
That was my next question. How does the program terminate?
A program never really terminates. Most programs or most instruction sets have what we call a halt instruction. And what the halt instruction does is to say, okay, let's stop everything in the processor. But the processor will wake up again, usually, when you have an interrupt. That we haven't talked about also.
So that's probably usually more handled by the operating system?
How to terminate the program?
Because the operating system keeps running.
Yes.
But an individual application that's on the operating system.
Oh, I see what you're saying. Okay, I see what you're saying. So when you're talking about a C or C++ program, you can call exit, EXIT, and that is called to terminate a program. Or when you get to the return of the main subroutine, that also quote unquote terminates a program. But these two are different mechanisms. When you execute a return in the main function of a C or C++ program, that only terminates the part that you have control over. But it returns back to a lower level part of your program where the C library can specify cleanup code, and then the program actually terminates. Okay? But that's the normal way of getting out of the program, is to use a return in the main function to return to whatever code starts off your program to begin with.
But from a hardware standpoint, even when that's done, the operating system still.
Yes, the operating system is still running. So to turn off a computer, as opposed as in like turning off the power supply of a computer, that means you have to access an I/O register of some kind to actually connect to the power supply to turn off the actual power supply to the whole computer.
So as far as the process is concerned, there's always some loop being processed.
Yes, as long as the computer is on, it's not necessarily doing it in a tight loop, because you can put your processor into a kind of hibernation mode where it is not doing anything, it doesn't clock, it doesn't really do any computation. But the moment you have an interrupt, due to the mouse event, due to your network card event, due to something else, that will wake up the processor and start it to tick again. And that's how your phone can save a lot of power, is not to stay in an infinite loop, like a tight loop, and ask, okay, am I being touched? Am I being touched? Am I being touched? It just goes sleep and go like, okay, it will ask the circuitry that is responsible for the touch screen circuitry and say, if you're getting touched, then let me know. Otherwise, I'm just gonna doze off. Yep.
So that's the same when your PC goes to sleep. It's listening, but it's not.
A part of your PC is still listening, but that part does not consume a lot of power. Okay, so we're putting a hold on control structure because okay, there's one more thing I want to show here. So the key is now here. Okay, what we really need to address is this little mux here. What is being used to control this mux and say, oh, don't continue to go to the next location. Instead, use the other path and change yourself to that particular value. That becomes the main question, is how do we switch between these two potential inputs into the data port of the program counter? That becomes the big question. Now, if you just want a tight loop, an infinite loop that has no possibility of exiting, we have the circuitry to do that already, okay? Because you can specify an instruction or memory location here that goes into one of the registers. Okay, I'm just following the path here. It goes into one of the registers, and then you can turn around and use the output of the register bank and feed that into the program counter. Is that okay? Now, obviously, we haven't hooked up the control lines and stuff like that, but the pathway does exist. But what is not clear to us is, how do we do conditional branches? In other words, when you deal with something like this in C and C++, what are we going to do about that in the architecture? The most basic form of conditions in a C or C++ program is a comparison. That is the most basic mechanism that can give you something that is either true or false to make a decision. So in C and C++, if you say if x is less than y plus x, okay, so let's just say that we have a very simple conditional statement that says if x is less than y, we want to increment x. If not, don't do anything. Okay, there's no else to this particular conditional statement. So if you think about this, okay, not even knowing assembly language programming, not even knowing the rest of the processor, something needs to do the plus plus sometimes, and other times we don't want to do it. In other words, to control which way to go, we need to look at the result of a comparison. Okay? Now we have touched on that a little bit because the borrow flag is one of those things that you can rely on and say, okay, what was the result of the comparison? You can use the borrow flag for certain things, but not everything. So we are going to, that's why we have to put a hold on the design of the processor so that we can finish up what is comparison and how do we compare signed versus unsigned numbers, then we can come back to the processor design and say, okay, how do we implement all that mechanism? Because those mechanisms eventually connects to this select port.
The ALU is going to keep record of that, or?
The ALU is responsible to set those conditions, but there are some additional circuitry that is needed to say, okay, which one am I using to switch the input into the program counter?
So it's like the ALU will keep record of a byte, let's just say,
Right.
and we need some sort of selector that will pick whatever bit.
Exactly. Yep. So since we are kind of running out of time, not completely, we'll have enough time to do one thing. But we are moving on to signed numbers and also how to compare. Okay. So this is signed numbers, and I have to put it into editing mode to highlight it, because I don't want to put a highlight here so that we know where we are at. Okay. So we want to talk about subtracting and comparing at this point. In other words, how do we know two numbers are the same? And I'm just going to talk about that first. Okay. How do we know whether two things are the same or not?
Your subtraction zero. I mean, the
Well,
addition zero.
the result of a subtraction is a 0. Okay. So I'm going to do it on my document camera. So after the exam, we'll continue with this discussion here. All right, so we will take a look at a subtractor. Okay, so I'm just, instead of using LogicSim, I'm doing it by hand. We'll just say that borrow in is a 0. We don't care about the borrow out at this point. And we have two numbers, x and y. Okay, so we are now calculating x minus y. So the output is x minus y. And for the sake of this argument, I'm going to split it into the individual bits. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay. So now I'm looking at the individual bits after an 8-bit subtraction, x minus y. And I want to see whether the result is 0 or not. Not whether a single bit is 0, I want to know whether the entire result is 0. Because if the result of x minus y is 0, I know x and y are the same. So I'm not interested in storing the result so much as to looking at the individual bits and say, is x and y are they the same number? Okay, that's the question. So now the question is, how do I know that? In other words, I want an output pin here, which is a single bit. We call it a Z flag, which is going to be a 1, but only if this result is all zeros. So what kind of a gate do I need here?
And with a zero. You add it with all zeros.
Okay, if you use an AND gate, that means if any one of the bits of the input is a 0, the output is going to be the same anyway. So you can have 0, 0, 0, 0, 0, 0, 0, 1, and the result would be the same as all zeros. That may not be what we want.
Not an OR gate?
We should start with the OR. Okay, so let's start with the OR. And we'll do it as a gigantic OR gate here. Looks like a smiley face to me. Okay, so we have a gigantic OR gate. Okay, but with the OR gate, the polarity of the output is not correct. Because with the OR gate, if any one bit of the result is a non-zero, then the output is non-zero, or 1 in this case. That's not what I want. I want the exact opposite. I want the output to be I want Z to be a 1 when the result of the comparison is a 0. Completely negated already. Just negate it, exactly. So this becomes a NOR gate, and that's one of the flags. Okay, the Z flag is really just a huge, gigantic NOR of all the individual bits after a subtraction. If the Z flag is a 1, it means those two numbers are the same. If the Z flag is a 0, it means those two numbers are not the same. Which one is bigger? Well, the Z flag doesn't tell you that. It can only tell whether they are the same or not. But this is our introduction to the flags that can help us determine which way to go. Because if you combine this with the LogicSim diagram that we have been looking at, the Z flag is one of the things that can go here. Which means after a subtraction, we can look at quote unquote the Z flag and say, okay, let's see whether we should just continue on with the next instruction or whether we have to rely on another register to tell me where to go. Is that making any sense so far? So this way we now have the ability to make conditional branches by using a flag that is indicating the result after a comparison as the selection bit to the box feeding the PC. Now we have a way to say, oh, sometimes we want to just continue on with the processing, and other times we want to go back to an earlier point or jump around to a later point. Yep.
Where would you put that in this diagram?
The Z flag?
Yeah.
Okay. The Z flag belongs to the ALU, which means the ALU is not quite done yet. Okay, this picture here is not quite done yet because in addition to the output, we also will need a bunch of flags. The Z is the first of all the flags, but we usually end up with 3 really important flags, but there are also some other not so important flags that I may not want to include in this picture. But the lecture, after the exam, the midterm number 1 next week, our focus will be shifted to subtracting and comparing. And we have maybe a minute left. So in this particular discussion here, we will talk about all of these quote-unquote flags. Okay, each flag is really just a single bit. Okay, if you don't like the term flag, just look at these as individual bits. Okay, so we'll have the carry flag, which is also the borrow flag. That one we have talked about already, right? Okay, so we're kind of good with that, but we need to go through some more discussion with that. We just talked about the 0 flag, so these are the 2 easiest ones to talk about. The sign flag and the overflow flag, they are useful in a certain way, but they're not really entirely that useful for comparison purposes, because those 2 need to be combined into the L flag later on. So these things we'll talk about later on next Thursday. And then we also have to talk about I may have moved things around to the wrong places because I want to see if, yep, this will still work, because we want to talk about signed versus unsigned numbers. So those are the things that we'll be starting to talk about next Thursday. And then once we're done with these topics, we'll go back and modify the architecture one more time, and then we'll finish it at that point so that we can actually run certain instructions with our little toy architecture. All right. Are there any questions about the exam itself? It's open book, open notes. You can bring anything that is either handwritten or printed prior to the test. Bring extra pieces of paper just in case you need those to turn in. Okay. And I usually don't say good luck, because I don't think luck should have anything to do with the test. Good luck.